In the mind, the solar system often feels close, almost compact. Planets appear lined up, distances seem manageable, and space feels filled. But in reality, everything is separated by vast, silent emptiness. Even the nearest worlds are unimaginably far apart. Light itself needs minutes, sometimes hours, to cross these distances. This is not a crowded system. It is a thin scattering of matter around one star. In this video, the true scale of the solar system slowly unfolds, from its farthest reaches to its blazing center. If this kind of quiet exploration helps you see the universe more clearly, consider liking the video and subscribing to the channel. The solar system begins, in this wide view, not with the sun itself but with the darkness around it. It exists as a small gravitational system inside the Milky Way, one galaxy among many in the observable universe. The Milky Way contains hundreds of billions of stars. Most of them lie at distances so great that ordinary language struggles to hold them. Light, which moves faster than anything else known in nature, takes years to cross the spaces between many stars. Against that scale, the solar system is not a large domain. It is a local structure, bound together by the gravity of one ordinary star, suspended in a galaxy that spreads far beyond direct human intuition. The Milky Way is a barred spiral galaxy, a vast rotating system of stars, gas, dust, and dark matter. Dark matter is the name given to unseen mass detected through gravity. Observations indicate that it helps hold galaxies together, though its exact nature remains uncertain. Within this galaxy, the solar system resides far from the crowded central bulge and far from the dramatic spiral arms as they are often pictured in drawings. It moves through a quieter region of the galactic disk. At a distance of roughly 26,000 light-years from the galactic center. That number sounds exact when written plainly, yet even it is an estimate refined by measurement and model. In this part of the galaxy, stars remain separated by enormous gulfs. The sky, seen from a place beyond Earth's atmosphere, appears dense with light, but physical space itself remains overwhelmingly empty. This emptiness matters because the human mind often imagines the solar system as a packed arrangement, with planets lined neatly near one another and the sun close behind them. Such images serve teaching, but they do not reflect scale. In reality, the solar system occupies a volume of space in which matter is spread thinly. Even where small bodies are common, vast distances separate them. Space is not a background into which worlds are placed like objects on a shelf. Space is the main fact. Matter is the exception. The solar system is therefore best understood first as a pattern inside emptiness, not as a cluster inside fullness. The Sun and everything that remains gravitationally tied to it travel around the center of the Milky Way together. This journey is not quick in human terms. One orbit around the galaxy takes roughly 230 million years. In that span, continents shift, species appear and vanish, climates rise and fall, and mountains lift and erode. While Earth measures days and seasons, the solar system itself follows a slower path through the galaxy, carrying its planets, moons, comets, and dust through changing interstellar surroundings. It does not sit still. It travels within a larger moving system. That larger setting includes the local interstellar medium, the thin material between stars. This medium contains gas, mostly hydrogen and helium, and fine dust grains. It is so thin that even the best earthly vacuum chambers still hold denser matter. Yet across immense distances, this sparse material becomes important. The solar system moves through a region of this medium sometimes called the local interstellar cloud. though the structure and boundaries of nearby clouds are still studied and described with some uncertainty. What matters here is not a fixed border drawn on a map, but a physical truth: the solar system exists inside a galactic environment. It is not isolated from the rest of the galaxy. It is immersed in it. The Sun continuously releases a flow of charged particles known as the solar wind. A charged particle carries electric charge, which allows it to respond strongly to magnetic fields. This outward flow pushes against the interstellar medium and creates a broad bubble-like region called the heliosphere. The heliosphere is not a solid shell. It is a changing region shaped by the balance between the solar wind and the pressure of interstellar space. It stretches far outward and helps shield much of the solar system from a portion of the high-energy radiation known as cosmic rays. Cosmic rays are fast-moving atomic particles that come from violent events and energetic environments in the galaxy and beyond. The heliosphere, therefore, marks one important way in which the solar system has a real physical presence inside the Milky Way. It is not only a family of orbiting bodies, it is also a moving zone of solar influence pressed outward into interstellar space. Even so, the heliosphere remains tiny compared with the galaxy around it. The Milky Way is measured in tens of thousands of light years. The main planetary region of the solar system occupies only a minute fraction of that scale. Even the farthest known reaches of the Sun's gravitational influence, however they are defined, remain local when compared with the distance to the nearest stars. Proxima Centauri, the nearest known star to the Sun, lies more than 4 light-years away. That fact alone reshapes the meaning of nearness. In common thought, the solar system may seem expansive. In galactic terms, it is a small clearing around one star, separated from the next clearing by a darkness so deep that even light requires years to cross it. This is why the true scale of the solar system is hard to grasp. The problem is not only size, the problem is contrast. The Sun appears large because it dominates the local system. The planets seem familiar because they belong to the same family. Yet the whole family is set inside a galaxy so large that ordinary comparison fails. If the solar system is imagined as a small house, then the Milky Way is not a larger town around it, but a continent of scattered lights separated by wilderness. And beyond the Milky Way lie other galaxies, themselves separated by still greater voids. In that wider context, the solar system takes on its proper character. It is not the center of anything larger than its own local gravity. It is a modest system in transit. Seen from this outermost perspective, the most important truth is calm and severe. The solar system is real, structured, and bound together, but it is surrounded at every level by vastness. It sits in the Milky Way as one stellar system among many. It moves through thin interstellar matter. It carries with it a bubble of solar influence. It remains small against the galaxy, and the galaxy remains small against the wider universe. The first step in understanding its size is therefore not to count its worlds, but to feel the scale of the emptiness that contains them. Far beyond the planets, beyond the broad paths of Neptune and the known belt of icy bodies, thought reaches toward a region that cannot be seen directly as a whole. This region is called the Oort cloud. It is not a cloud in the sense of a bright mist or a dense bank of vapor. It is the name given to a vast swarm of icy objects thought to surround the solar system at extreme distance. The idea comes from the paths of long-period comets, especially those that enter the inner solar system from many different directions. Their orbits suggest a distant reservoir of frozen bodies, weakly bound to the Sun and spread through a nearly spherical volume of space. Observations support this general picture. The exact structure, total population, and outer limit remain uncertain. This distance is the first challenge. In the planetary region, scale already strains intuition. In the Oort cloud, ordinary planetary measures begin to feel too small. Bodies there may orbit at distances of thousands to perhaps tens of thousands of astronomical units from the Sun, and some models extend the outer region even farther. An astronomical unit is the average distance between Earth and the Sun. It is a useful measure inside the solar system. But here even that unit starts to multiply into long sequences. Light itself takes many hours to travel from the Sun to the outer planets. To the inner part of the Oort cloud, light would take many days. To the farther parts, it would take weeks or months. The Sun, from there, would no longer rule the sky as a blazing disk. It would appear as an unusually bright star, still dominant in gravity, but visually reduced by distance almost beyond emotional recognition. This is where the solar system stops resembling a compact set of planetary tracks and becomes something much looser. The Oort cloud is not a ring like the orbit lines often drawn in simple diagrams. It is thought to form a rounded shell or a deeply extended sphere. That shape matters. The major planets orbit in roughly the same flat plane, a broad disk left over from the rotating cloud of gas and dust that formed the Sun. The Oort cloud does not follow that same flatness. Its objects appear to come inward from many angles, which is one reason astronomers infer a more spherical distribution. Over immense spans of time, the gravity of giant planets, passing stars, and the wider tidal pull of the Milky Way seem to have helped scatter icy bodies outward and lift them into every orientation. The word tidal here means a change in gravitational pull across distance. Just as the Moon raises tides on Earth by pulling slightly more strongly on one side of the planet than the other, the galaxy itself exerts a weak but persistent tidal effect across the solar system. In the inner system, the Sun's pull dominates so strongly that this galactic effect is negligible for ordinary motion. At the great distances of the Oort cloud, the balance becomes more delicate. A passing star does not need to come especially near in human terms to disturb such distant bodies. It only needs to shift the gravitational balance slightly. Over millions of years, such nudges matter. This makes the Oort cloud a region of weak attachment. Its objects belong to the solar system, yet they inhabit a boundary where belonging grows thin. The Sun still holds them, but not with the same firm rule it exerts over Earth or Jupiter. A small disturbance can alter a long quiet orbit and send an icy body inward. Some of the comets that later appear in the skies of the inner solar system may begin such journeys in this remote storehouse. They spend most of their existence in cold darkness, moving slowly through immense arcs, then briefly approach the Sun, warm, brighten, grow tails of gas and dust, and return outward or leave forever if gravity redirects them enough. Here the scale of emptiness becomes even more important than the number of objects. The Oort cloud may contain billions or even trillions of icy bodies, depending on model assumptions, but that does not mean crowding. The volume of the region is so vast that individual objects remain separated by enormous distances. Even if many bodies are present, each one occupies its own loneliness. The human tendency is to hear large numbers and imagine closeness. In this outermost realm, large numbers still dissolve into sparse distribution. An icy object may travel through darkness for ages without any nearby companion visible at all. The region is populous in count and empty in lived spatial experience. Its material is thought to consist mainly of icy remnants from the early solar system. Water ice is likely present, along with frozen carbon dioxide, methane, ammonia, and rocky material mixed within. These are leftovers from formation, bodies that never became planets. In the warmer inner region of the young solar system, Volatile substances such as water and methane could not easily remain frozen. Farther from the Sun, such materials condensed more readily. Many small icy bodies formed there. Later, the giant planets, especially Jupiter and Saturn, disturbed countless objects through repeated gravitational encounters. Some were thrown out of the solar system entirely. Some were pulled into more distant but still bound paths, helping populate the remote cloud. This broad origin story fits well with current models, though details of timing and efficiency remain active areas of study. No spacecraft has travelled through the Oort cloud in the full sense of crossing its suspected depth and returning direct information about its population. The most distant human-made probes, Voyager 1 and Voyager 2, have passed beyond the heliosphere into interstellar space, but they remain far closer than the classical outer Oort region proposed in many models. This means that the Oort cloud is known indirectly. It is inferred from comet behavior, from orbital mathematics, and from theories of solar system formation tested against observation. This indirect knowledge is strong enough to make the Oort cloud a central concept, yet it also requires caution. Observations indicate that such a distant reservoir exists. It remains uncertain exactly how densely it is filled, how far it extends, and how sharply it fades into the background of interstellar space. That fading matters because the Oort cloud is not simply an object with a crisp border. It is better understood as an outer realm of diminishing solar control. At some point, the Sun's gravity still outweighs the pull of other stars for a given icy body. Farther still, outside stable solar possession, interstellar space begins in a more practical sense. The transition may not resemble a wall or a line. It may be gradual, statistical, and dependent on how one defines membership in the solar system. One may define it by orbit, by gravitational dominance, or by the reach of the Sun's wind and magnetic influence. These are related but different ideas. The Oort cloud belongs mainly to the question of gravity. In this region, the solar system reveals one of its deepest truths. It is not shaped only by the bright bodies close to the Sun. It also includes this almost invisible outer memory, a far-flung archive of early icy fragments held in a sphere of cold patience. The Sun is still the centre, but the system around it has already become diffuse, fragile, and difficult to map. The farther one moves from the warmth of the star, the less the solar system resembles a tidy arrangement, and the more it resembles a vast fading field of possibility. Here, at its outermost suspected edge, size becomes less a matter of visible objects and more a matter of silent reach. Inside the distant spherical reserve imagined for the Oort cloud, but still far beyond the classical orbit of Neptune, the solar system takes on a different shape again. Here the pattern is not a sphere and not a narrow planetary track. It is a broad, restless region known as the scattered disk. This is a population of icy bodies moving on elongated, often tilted orbits that carry them to great distances from the Sun while still bringing them, at one point in each long path, back toward the outer planetary zone. The name comes from process rather than appearance. These bodies are thought to have been scattered outward by gravitational encounters, especially with Neptune, and their present motions still preserve the mark of that history. The scattered disk is not sharply separated from neighbouring outer populations in every case. Nature rarely arranges itself into clean educational categories. Some bodies fit the region well, while others sit near the edge between one class and another. Still, the broad meaning is clear. A scattered disk object usually travels on an orbit that is more stretched than the near-circular paths followed by the major planets. Its distance from the Sun changes greatly over the course of one revolution. It may spend most of its time in deep cold far beyond Neptune, then return inward to a point where Neptune's gravity can still affect it. This continuing possibility of disturbance is important. It means the region is not only ancient in origin, but also dynamically alive. A dynamical region is one defined by motion and gravitational interaction. In the scattered disk, motion tells the story. The bodies there do not occupy a simple band of equal distance. They move through space on paths of great length, with orbital periods that may last thousands of years or much more. Many of these objects also travel on paths inclined relative to the flat plane in which most planets orbit. Inclination is the angle between one orbit and a reference plane. In plain terms, it means that some of these icy worlds move above and below the main planetary level instead of staying close to it. This gives the outer solar system a deeper thickness than the usual flat diagrams suggest. That thickness remains mostly empty. Once again, the mind hears of a region full of objects and imagines a crowded field. The reality is still one of vast separation. A scattered disk object is not passing close to others in a busy current. It is following a lonely route through an immense volume of darkness. Even where many such objects exist, the space between them is enormous. The region feels diffuse because it is diffuse. Its identity comes from shared orbital character, not from physical closeness. Neptune is central to this story. Although the scattered disk stretches far beyond Neptune, many of its objects owe their paths to repeated past encounters with that planet. Neptune circles the Sun at a distance, where its gravity can still reshape smaller icy bodies over long timescales. When a small object passes close enough, the exchange of energy changes its orbit. One encounter may lengthen the path, another may tilt it, over many millions of years. A body that once moved in a more regular outer orbit can be driven into a scattered one. Some objects are eventually ejected from the solar system altogether. Some settle into distant stable patterns. Some remain in these elongated paths that still carry the memory of Neptune's influence. This process helps explain why the outer solar system is not a simple frozen leftover from formation. It is also a record of migration and rearrangement. Current models indicate that the giant planets did not necessarily remain exactly where they first formed. In the early solar system, large planets and countless smaller icy bodies exchange gravitational influence in a broad reshaping phase. Neptune likely moves outward from its earlier position, disturbing material as it goes. As it migrates, it scatters some objects inward, some outward, and traps some in orbital resonances. A resonance is a repeating gravitational pattern in which one body completes a certain number of orbits, while another completes a different but related number. Such patterns can protect an orbit or destabilize it, depending on circumstances. In the scattered disk, the signature of this ancient movement still survives in the distribution of orbital shapes. Some well-known distant objects belong to this broad category or lie close to it. Eris, for example, follows a strongly elongated path and spends much of its time far beyond Neptune. It is one of the largest known bodies in this remote region. Its discovery helped sharpen the question of how outer solar system bodies should be classified, which in turn shaped the modern definition of a planet. Yet in terms of physical experience, even an object like Eris remains not the centre of the region, but only one solitary member of a sparse population. The scattered disk is not organised around a dominant body in the way the planetary system is organised around the Sun. It is a family resemblance of many lonely orbits. The conditions there are severe but quiet. Sunlight is weak. Surface temperatures remain extremely low. Ices that are unstable closer to the Sun can persist for immense spans of time. The bodies themselves are thought to be mixtures of water ice, other volatile ices, and rock. Their surfaces may darken over time under the action of radiation, micrometeorite impacts, and slow chemical change. Because they are so distant and so small, observations remain limited. Telescopes detect only a fraction of what likely exists. Smaller bodies are especially hard to find. This means the observed population is only a sample, weighted toward the larger and brighter members. It remains uncertain exactly how many scattered disk objects exist in total, and how their sizes are distributed below current detection limits. Even with this uncertainty, the scattered disk reveals something precise about scale. The solar system at this distance is no longer well described by the tidy image of evenly spaced planets. It becomes a realm where gravity has flung remnants outward into stretched paths that occupy huge reaches of space. The major planets remain important as shapers, but they are now behind the main visual idea. What matters here is the architecture of aftermath. The scattered disk is a product of gravitational history made visible in motion. The region also shows that distance alone does not define an outer zone. Two bodies can each lie far beyond Neptune and still belong to different dynamical groups because their orbits behave differently. One may move in a more settled band. Another may continue to interact with Neptune across deep time. The scattered disk is therefore a lesson in pattern rather than mere remoteness. It is not only far away, it is far away in a particular way. Its bodies carry stretched, tilted, vulnerable paths shaped by long conversation with gravity. In this outer region, the scale of the solar system continues to widen, but its meaning also becomes richer. The Sun still binds these distant objects, yet Neptune still reaches them indirectly, and time itself acts as an architect. The scattered disk appears not as a finished structure, but as a moving archive of outward displacement. It is thinly populated, weakly lit, and spread across distances that turn single orbits into epics of cold recurrence. Here the solar system is already telling its history not through bright surfaces or crowded worlds, but through the geometry of motion in the dark. Closer to the Sun than the scattered disk, but still far beyond Neptune, the outer solar system settles into a broad flattened region known as the Kuiper belt. This belt is often described as a ring of icy bodies left over from the formation of the planets. That description is useful, but it can mislead if imagined too simply. The Kuiper belt is not a bright band packed with objects brushing past one another. It is a vast, cold expanse in which many small worlds follow long paths around the Sun while remaining separated by immense stretches of emptiness. It belongs to the same general outer family as the scattered disk, yet it is more orderly in overall structure. Its bodies usually move on less extreme orbits, and the region as a whole reflects a calmer pattern of residence. The belt begins beyond Neptune and extends outward for many astronomical units. Even that statement needs patience to absorb. 1 astronomical unit is the average distance between Earth and the Sun. In the inner solar system, this measure helps compare the paths of the rocky planets. In the Kuiper belt, it becomes a way of speaking about a broad zone so large that each extra step outward still covers an enormous gulf. The belt occupies a region where sunlight is greatly weakened. The Sun is still the central master of motion, but its warmth has thinned to a faint input, and its light no longer fills space with the force familiar near Earth. A surface there may still reflect sunlight, but the source is remote, small in the sky, and poor in heat. This weak sunlight helps preserve ancient material. The bodies of the Kuiper belt are thought to be made largely of ice mixed with rock and organic compounds. Organic compounds here do not mean life. They mean carbon-based molecules formed through chemistry in cold environments. Water ice is common, along with other frozen substances such as methane, nitrogen, and ammonia on some objects, over long spans of time. Radiation from the Sun and from the galaxy can alter exposed material at the surface, darkening it or reddening it through slow chemical processing. The result is a population of distant bodies that preserve clues to early solar system conditions, while also carrying the marks of age and exposure. Many Kuiper Belt objects are small, but some are large enough to be rounded by their own gravity. Pluto is the best-known example. Once counted among the major planets, Pluto is now classified as a dwarf planet because it is round and orbits the Sun, yet does not dominate the neighbourhood around its orbit in the way the 8 major planets do. This change in classification reflects improved understanding, not a shrinking of Pluto itself. Pluto remains one of the largest known members of the Kuiper Belt, accompanied by moons and marked by a complex surface of ice plains, mountains of water ice, hazes, and seasonal changes. Other large bodies, such as Haumea and Makemake, also inhabit this distant region, each with its own unusual features. Yet even these prominent names must be held in perspective. The Kuiper Belt is not defined by a few celebrity worlds. It is defined by the spread of countless icy remnants across a huge volume of space. The belt is flattened rather than spherical because it preserves more of the original disk-like structure from which the solar system formed. The young sun emerged from a rotating cloud of gas and dust. As that cloud collapsed, its spin helped flatten material into a disk. The planets formed within that disk, and many smaller leftovers remained. In the Kuiper Belt, this ancient geometry remains visible. Most objects orbit in roughly the same broad plane as the planets, though not all follow perfectly circular or perfectly level paths. Some belong to a relatively calm group with modest inclinations and less stretched orbits. Others are more excited, meaning their paths are more tilted or more elongated. This internal diversity suggests a history shaped not only by original formation, but also by later gravitational rearrangement. Neptune again plays a major role. Some Kuiper Belt objects are caught in resonances with Neptune. A resonance is a repeated orbital relationship in which the timing of motion creates a stable pattern. Pluto is a famous example. For every 3 orbits Neptune completes, Pluto completes 2. This pattern prevents close encounters even though the paths, when projected onto a flat diagram, may seem to cross. Resonance acts like a rhythm in gravity. It does not remove motion. It organizes motion over long timescales. Many objects in the Kuiper Belt belong to such resonant groups, and their existence offers strong evidence for Neptune's outward migration in the early solar system. As Neptune moved, its resonances swept through the outer disk, capturing some bodies into regular patterns while scattering others away. This is one reason the Kuiper Belt matters so much scientifically. It is not only a storehouse of ancient material, it is also a record of planetary migration. The present arrangement of distant icy bodies carries memory of how the giant planets shifted and settled. Observations of Kuiper Belt orbits support the idea that the outer solar system was once more mobile than it appears today. The belt, though calm in present visual impression, is therefore an archive of earlier movement. Still, the first truth of the region remains its emptiness. Popular illustrations often show the Kuiper Belt as a dense band full of nearby chunks of ice and rock. This is convenient for drawing, but false to scale. Even where many objects exist, the distances between them are enormous. A spacecraft passing through the outer solar system does not weave through a crowded debris field. It travels through vast open darkness where encounters with solid bodies are exceedingly rare unless planned with extraordinary precision. The New Horizons mission, after flying past Pluto, continues into the Kuiper Belt not through congestion, but through space so empty that individual targets must be selected and reached with careful calculation over years. The New Horizons observations of Pluto and the smaller body Arakoth offer a glimpse into the nature of this region. Arakoth, visited in the Kuiper Belt after the Pluto encounter, appears to be a contact binary, meaning two smaller bodies join gently to form one larger object. Its shape and surface suggest a quiet history with low-speed assembly, supporting the view that some Kuiper Belt objects preserve very ancient conditions from the solar system's formation. This does not mean every object there is unchanged in every respect, but it does show that the outer cold has protected delicate records of the past. In the Kuiper Belt, the solar system feels broad, thin, and persistent. The giant planets are now inward enough to become distant influences rather than immediate presences. The Sun still governs every orbit, yet its light has weakened into a remote illumination. Bodies remain frozen, spaced far apart, and bound into a disk that stretches across a realm almost empty to any direct traveller. Here the true scale of the solar system becomes easier to understand through contrast. There are many objects, yet little crowding. There is structure, yet that structure is mostly space. The Kuiper Belt is not a wall of material at the edge of the known system. It is a cold plain of separated remnants, wide enough to humble instinct and quiet enough to preserve the early history of worlds. Moving inward from the Kuiper Belt, the solar system becomes more structured again as the orbit of Neptune comes into focus. Neptune marks the outer boundary of the region dominated by the giant planets. It is the most distant of the 8 major planets, circling the Sun at an average distance of about 30 astronomical units. Even this number, when translated into experience, resists easy understanding at such a distance. Sunlight is reduced to a faint glow compared with the brightness known near Earth. The Sun appears small, yet still far brighter than any other star in the sky. Its gravitational hold remains firm, guiding Neptune along a long, slow path that takes roughly 165 Earth years to complete a single orbit. Neptune is classified as an ice giant. This term distinguishes it from the gas giants Jupiter and Saturn. An ice giant contains a larger proportion of substances such as water, ammonia, and methane in forms compressed by high pressure and temperature inside the planet. These materials are not icy in the everyday sense at depth, but the term reflects their chemical nature compared with hydrogen and helium, which dominate the gas giants. Neptune's outer atmosphere shows a deep blue colour, caused largely by methane absorbing red light and allowing blue light to scatter back into space. Beneath that visible layer, pressure rises, temperature increases, and matter enters states that are difficult to recreate directly in laboratories. Observations and models indicate a complex interior, but the exact details of structure and composition remain an area of active research. The scale of Neptune itself is significant. It is many times larger in diameter than Earth, and far more massive. Yet in the context of the solar system's total volume, even a giant planet occupies only a tiny fraction of space. This contrast is essential. A large world does not fill its orbital region. Neptune moves through a path so vast that the planet itself is a small presence within it. The distance between Neptune and its nearest planetary neighbour, Uranus, is not a narrow gap but a wide expanse measured in many astronomical units. Within that expanse there is no continuous chain of material linking one planet to the next. There is only space, crossed slowly by each world in its own long journey around the Sun. Neptune's gravity plays a defining role in shaping the outer solar system. It influences the Kuiper belt, captures objects into resonance, and helps maintain the scattered disk through ongoing interaction with bodies that pass close enough during their orbits. This reach does not mean constant contact. Instead, it reflects a statistical influence across time. A small object may complete many orbits without a close encounter, then experience a shift during a distant pass that alters its path for millions of years to come. Neptune therefore acts less like a gate and more like a long-term sculptor, shaping orbital patterns gradually through repeated gravitational effects. The planet also possesses a system of moons and faint rings. Its largest moon, Triton, is of particular interest. Triton orbits Neptune in a direction opposite to the planet's rotation, which suggests it did not form in place. Observations indicate that Triton was likely captured, possibly originating from the Kuiper belt before becoming bound to Neptune. This capture would have been a complex event involving energy exchange, and it likely altered the original system of moons that Neptune once possessed. Triton today shows signs of geological activity, including nitrogen ice and possible cryovolcanism, where materials erupt at low temperatures compared with volcanic processes on Earth. Even here, in a region so far from the Sun, internal energy and orbital history combine to produce change. Neptune's atmosphere is dynamic despite the weak solar input. Winds there can reach speeds of more than 1,000 kilometers per hour, among the fastest measured in the solar system. The source of this energy is not fully understood. The planet emits more heat than it receives from the Sun, suggesting that internal processes contribute to atmospheric motion. Storm systems appear and fade, and high clouds of methane ice drift above deeper layers. These features remind observers that distance from the Sun does not imply stillness. Even in the cold outer region, planets remain active systems governed by both internal and external forces. The orbit of Neptune defines an important transition in the solar system. Outside its path, the population shifts toward the distributed bodies of the Kuiper belt and the more irregular orbits of the scattered disk. Inside its path, the solar system begins to change character again. The spacing between major planets remains large, but the influence of the Sun grows stronger. Light becomes brighter, and orbital periods shorten. Neptune therefore stands at a threshold. It is the last major planet before the solar system moves inward toward regions where planetary influence overlaps more closely and where sunlight becomes a more dominant factor in shaping conditions. Yet even here, the lesson of scale remains constant. Neptune may be a giant world, but it does not reduce the emptiness of its surroundings. The region it inhabits is still vast beyond ordinary imagination. If Neptune were removed, the space it occupies would not collapse or fill. It would remain a wide arc of emptiness around the Sun. The presence of a planet does not define the size of its orbit. The orbit defines the space in which the planet moves, and that space is enormous. From a distant viewpoint, Neptune traces a slow circle around the Sun, accompanied by its moons and embedded in a larger pattern of outer solar system bodies. It is one member of a broader system, not an edge or a barrier. Beyond it lie the cold plains of the Kuiper belt and the scattered disk, and farther still the uncertain reaches of the Oort cloud. Within it lie the other giant planets and the inner worlds. At this stage in the inward journey, the solar system still feels wide and sparse, but a gradual tightening begins. The distances remain immense, yet the pattern becomes more layered, more influenced by the presence of large planets, and more structured by repeated gravitational relationships. Neptune's realm is therefore both remote and connected. It stands far from the Sun in physical distance, yet it remains deeply tied to the history and structure of the entire system. Its gravity reaches outward to shape distant icy bodies, and inward to contribute to the balance among the giant planets. It moves in darkness compared with Earth, yet it is not isolated. It is part of a continuous field of motion that extends from the faintest outer remnants to the bright central star. In this region, the solar system reveals how even its farthest major worlds exist not as isolated points, but as participants in a wide and delicate gravitational network spread across a vast and mostly empty domain. Inside the path of Neptune, the next great region belongs to Uranus. Though closer to the Sun than Neptune, Uranus remains deeply remote by human standards. It circles the Sun at an average distance of about 19 astronomical units, which means it receives only a small fraction of the sunlight that reaches Earth. At that range, the Sun still governs the planet completely in gravitational terms, but visually it is much reduced, bright yet distant, no longer the large commanding disk seen from the inner worlds. Uranus takes about 84 Earth years to complete one orbit. A human life can pass during a single Uranian year, and this alone begins to show how widely the solar system opens in its outer half. Uranus is the second of the two ice giants. Like Neptune, it differs in composition from Jupiter and Saturn. Hydrogen and helium are still present, especially in the atmosphere, but a larger share of the planet's mass appears to consist of heavier substances such as water, ammonia, and methane in hot, dense forms beneath the visible cloud tops. These materials are compressed under immense pressure and do not resemble ordinary ice as found in a freezer or on a winter surface. The term points instead to chemical category. Inside Uranus, matter exists in states shaped by conditions so extreme that common experience offers little direct analogy. Models suggest layered regions, including an atmosphere, a deep mantle rich in compressed volatile materials, and a central rocky component. The exact details remain uncertain because direct measurement of the deep interior is limited. The planet's pale blue-green colour comes largely from methane in its upper atmosphere, which absorbs red wavelengths of sunlight. This colour is softer than Neptune's deeper blue, and the visible atmosphere often appears calmer in ordinary images. For a long time, Uranus was thought to be less active than Neptune, but modern observation reveals cloud structures, seasonal changes, and storms, though often subtler than those of its outer neighbour. The relative quiet of its visible appearance should not be mistaken for simplicity. Uranus is a full planetary system, complex in motion and layered in structure, set in a region where sunlight is weak and temperatures are low. Its most unusual large-scale feature is the tilt of its rotation axis. Uranus spins with its axis tipped by about 98 degrees relative to the plane of its orbit. In plain terms, it rotates almost on its side. This means that over the course of its long year, each pole spends decades facing toward the Sun, and then decades facing away. Seasons on Uranus therefore unfold in a way unlike those on Earth. They are not quick alternations of moderate difference. They are long, slow shifts in solar exposure affecting an entire hemisphere for years at a time. This extreme tilt is likely the result of a major event in the early solar system, perhaps one or more giant collisions during planet formation, though the exact history remains uncertain. That tilted rotation changes the geometry of the whole local system. Uranus has rings and many moons, and these are arranged around the planet's equator. Because the equator is so strongly tilted, the ring system appears turned over relative to the usual image of a flat planetary disk, aligned neatly with the solar system. This offers a quiet reminder that while the solar system has an overall flatness inherited from its formation disk, local systems can still differ dramatically in their internal orientation. Uranus obeys the Sun, yet it presents itself sideways within that wider order. The rings of Uranus are dark and narrow compared with the bright, broad rings of Saturn. They are made of particles ranging in size from dust to larger chunks, orbiting in thin bands around the planet. These rings do not fill the surrounding space. Like every other ring system, they occupy an extremely small fraction of the volume around the planet. Their beauty lies not in abundance of matter, but in arrangement. Seen at true scale, even ring systems are delicate structures within vast emptiness. The moons are also spread across wide distances. Miranda, Ariel, Umbriel, Titania, and Oberon, among others, circle Uranus in quiet regularity, each separated from the next by large gaps of open space. A planetary system, even when rich in moons, remains mostly vacuum. Uranus reveals another important feature of solar system scale. Distance does not merely change brightness, it changes tempo. The farther outward one moves, the slower orbital motion becomes. Kepler's laws describe this relation. In simple terms, planets farther from the Sun travel more slowly and take longer to complete their paths. Uranus therefore moves around the Sun at a pace suited to its remoteness. It still travels quickly in ordinary units, many kilometers each second. Yet its circuit is so large that the full journey takes decades. Slowness in astronomy is often a matter of path length rather than weak motion. Uranus is not drifting idly. It is moving steadily through a giant orbit. This slower tempo shapes observation. Since its discovery in the 18th century, Uranus has not yet completed many full orbits under modern scientific study. Human astronomy, though powerful, has watched only a small fraction of its long-term seasonal and atmospheric cycles. This means that some processes on Uranus are known only in partial form. Observations indicate changing cloud activity and seasonal behavior, but a full record across many Uranian years does not yet exist. The planet therefore stands as a reminder that the solar system is not only large in distance, but also large in time. To understand remote worlds fully, human observation must persist across generations. Its magnetic field adds another layer of strangeness. Uranus possesses a magnetic field that is strongly tilted relative to its rotation axis and offset from the planet's center. A magnetic field is the region where magnetic forces act, generated in planets by moving electrically conductive material inside them. On Earth, this field is relatively well aligned with the rotational axis. On Uranus, the geometry is much more irregular. This creates a magnetosphere, the region shaped by the planet's magnetic field, with a lopsided and changing structure as Uranus rotates. Such features show that even in a distant, dimly lit zone, planetary physics remains rich and complex. Yet despite all this complexity, Uranus remains a small object compared with the space it inhabits. Between its orbit and those of Neptune and Saturn stretch vast distances that no atmosphere, ring, or moon system can fill. The emptiness between planets remains one of the defining truths of the solar system. The planets are not beads touching on a string. They are isolated worlds separated by enormous spans of darkness, each carrying its own system, each still only a small concentration of matter inside a huge orbital domain. In the realm of Uranus, the solar system feels quieter than in the regions farther out, not because there is less structure, but because the structure has settled into a slower rhythm. Neptune's distant influence fades behind. The Kuiper belt lies outward in colder obscurity. Here, one immense planet turns on its side beneath faint sunlight, carrying rings and moons through a broad and nearly silent region. This sun is still the ruler, but its warmth is weak. Its pull expressed through long periods and measured motion. Uranus shows that the true scale of the solar system is not only in the number of kilometers between worlds, it is also in the stretching of seasons, the length of years, and the thinness of matter across a domain that remains overwhelmingly open. Farther inward, the solar system arrives at the realm of Saturn. Here the darkness of the outer system remains, yet the Sun has grown stronger than it is at Uranus and Neptune. Saturn orbits at an average distance of about 9.5 astronomical units from the Sun. That still places it far beyond the orbit of Earth, in a region where sunlight is only a small fraction of the light received by the inner planets. Even so, compared with the deep outer system, this is a brighter province. The Sun appears more forceful, shadows are stronger, and the tempo of orbital motion begins to quicken. Saturn completes one orbit in about 29 Earth years, still slow in human terms, but much quicker than Uranus or Neptune. The great outward spread of the solar system is still unmistakable, yet a gentle tightening has begun. Saturn is a gas giant, composed mostly of hydrogen and helium. Unlike the rocky planets, it has no solid surface on which one might stand. Its visible form is the top of a deep atmosphere that thickens into layers of cloud and gas under increasing pressure, eventually merging into fluid states of matter below. At greater depth, pressure and temperature rise so strongly that hydrogen is thought to enter a metallic state, in which it behaves as an electrical conductor. This interior helps generate Saturn's magnetic field. The planet likely also contains a central concentration of heavier elements, though the exact size and composition of the core remain uncertain. What is clear is that Saturn is enormous in diameter and mass, yet low in average density for a planet. It is a giant, but a giant made largely of light elements. Its appearance is often described as serene. Broad pale bands wrap around the globe, and cloud patterns shift with storms, jet streams, and seasonal changes. The atmosphere is active, but from a distance it can seem calmer than Jupiter's more dramatic face. That calm visual impression suits the pace of this region. Saturn inhabits a zone where the solar system still feels spacious and cold, but no longer so remote that sunlight loses all force. The planet shines because it reflects that sunlight from clouds of ammonia ice and other atmospheric particles, while also radiating heat left from its formation and generated by slow contraction. The most famous feature of Saturn is its ring system. The rings appear broad and luminous, one of the most striking structures in the solar system. Yet they also offer one of the clearest lessons in scale. From a distance, they seem like solid bands. In reality, they are made of countless particles, mostly water ice, ranging from tiny grains to larger blocks. They orbit Saturn in a thin plane, each following the laws of motion around the planet. The rings are very wide compared with Saturn's diameter, but astonishingly thin in comparison with that width. In some places they are only tens of meters thick, though they spread across hundreds of thousands of kilometers. This is one of the quiet marvels of celestial structure. A vast-looking system can contain little material when spread across enough space. The rings are divided into named regions and gaps, shaped by gravity, collisions, and resonances with Saturn's moons. A resonance, in this setting, is a repeating gravitational relationship that can herd particles, clear lanes, or maintain wave patterns. Some moons orbit beyond the main rings and help confine narrow ringlets, while others influence the sharp edges of ring regions. The result is not a static decoration, but a living dynamical system, always in motion, always rearranging itself on scales from the microscopic to the planetary. Observations indicate that the rings are made mostly of relatively clean water ice, which gives them their brightness, though dust and darker material are also present. Their exact age remains debated. Some evidence suggests they may be younger than Saturn itself, while other interpretations leave room for greater antiquity. It remains uncertain how long the present bright ring system has existed in its current form. Saturn's moons form a second great system around the planet. More than 100 moons are known, though many are tiny and irregular. The larger moons reveal an extraordinary range of worlds. Titan is the largest and most substantial, with a dense atmosphere richer in nitrogen than any moon elsewhere in the solar system. Methane and ethane exist there in liquid form at the surface, creating lakes, seas, clouds, and rain in a cold hydrocarbon cycle that in some ways resembles Earth's water cycle. Though under profoundly different conditions, Enceladus, much smaller, sends plumes of water-rich material into space from fractures near its south pole, indicating a subsurface ocean beneath an icy crust. Other moons show heavily cratered ancient surfaces, mixed ice and rock interiors, and signs of past or present geological activity. These moons remind the observer that a planet is not a single object but a center of a local system. Saturn's gravity binds moons, rings, dust, and magnetic influence into a layered domain. Yet even this rich system occupies only a tiny island in the solar system's total volume. The space between Saturn and Jupiter inward, and between Saturn and Uranus outward, remains immense. A moon system can feel crowded when shown in diagrams, but in true scale the moons orbit through large separations, and the planet itself remains a compact body within a huge orbital lane around the Sun. Saturn also helps reveal the relation between beauty and emptiness. The ring system is perhaps the clearest example. It looks dense and complete, but the total mass of the rings is small compared with the mass of a major moon. Their splendor comes from arrangement, from reflective ice, from geometry and light. This is true more broadly across the solar system. Visual richness does not require great quantity of matter. Thin structures, spread across large spaces and lit at the right angle, can become the most memorable forms. The planet's magnetosphere extends far into surrounding space, shaped by the solar wind and by material from moons and rings. Charged particles move within this magnetic environment, creating radiation belts and auroral displays near the poles. These invisible structures add another level of scale. Saturn is not only the globe and its rings, it is also a larger region of influence extending outward, interacting with sunlight, plasma, and the broader flow of the solar system. Even so, this region too fades quickly against the size of Saturn's orbit around the Sun. At Saturn, the inward journey reaches a place where grandeur becomes easier for the human mind to see. The planet is large, the rings are luminous, the moon system is varied, and sunlight is strong enough to sculpt vivid contrasts. Yet the deeper lesson remains unchanged. Saturn does not make the solar system feel full. It makes the emptiness around structure more visible. A magnificent local system turns slowly within a vast orbital path, and beyond its beauty lies the same deep spacing that defines all the regions so far. Saturn's realm is rich, delicate, and expansive, but it is still mostly space, with matter gathered into a few shining forms. Inward from Saturn, the solar system enters the realm of Jupiter. Here the Sun grows stronger again, and the broad architecture of the planetary system becomes more forceful in its expression. Jupiter orbits at an average distance of a little more than 5 astronomical units from the Sun. This still places it far beyond Earth, but much closer than Saturn, Uranus, or Neptune. At this distance, sunlight is brighter, orbital motion is faster, and the relation between the planet and the rest of the solar system becomes more immediately important. Jupiter completes one orbit in nearly 12 Earth years. That period remains long by human standards, yet in the outer solar system, it marks a clear shift toward shorter cycles and stronger solar presence. Jupiter is the largest planet in the solar system by far. Its diameter exceeds that of Earth many times over, and its mass is greater than the mass of all the other planets, combined by more than 2 times. This fact gives Jupiter a special place in the structure of the system. It is not simply one giant among several. It is the dominant planetary mass. Only the Sun truly outweighs it in local gravitational importance. Even so, Jupiter remains tiny compared with the size of its orbit. The planet is enormous, but the space through which it moves is vastly larger still. This contrast between planetary size and orbital emptiness remains one of the essential truths of scale. Like Saturn, Jupiter is a gas giant made mainly of hydrogen and helium. It has no solid surface in the ordinary sense. Its visible face is the upper part of a deep atmosphere marked by cloud bands, storms, and swift winds. These bands arise from powerful jet streams flowing in opposite directions. Their colours come from chemistry in the upper atmosphere and from the effects of sunlight on trace compounds, though the exact causes of some colour variations remain under study. Below the cloud tops, pressure rises steadily until the familiar distinction between gas and liquid loses meaning. Deeper still, hydrogen is thought to enter a metallic state, helping generate Jupiter's immense magnetic field. A central core of heavier material may be present, though its structure and sharpness remain uncertain. Jupiter's atmosphere presents the most dramatic visible weather in the solar system. The Great Red Spot, a giant storm larger than Earth, has persisted for centuries. Though it changes in size and character over time, other storms form, merge, fade, and reappear across the broad cloud belts. Lightning flashes within deep clouds. Auroras glow near the poles where charged particles follow the planet's magnetic field into the upper atmosphere. These features make Jupiter look alive with motion. And indeed it is. Yet the true significance of Jupiter lies not only in its own activity. It lies in the way its mass shapes the wider system. A body of such mass exerts powerful gravitational influence. Jupiter affects nearby asteroids, helps create gaps and concentrations in the asteroid belt, perturbs the paths of comets, and participates in the long-term stability of planetary motion throughout the solar system. Its gravity can redirect small bodies inward toward the Sun or outward into colder space. It can capture temporary companions and alter orbital timing through resonances. A resonance, in this context, is a repeated gravitational pattern created when orbital periods fall into simple numerical relationships. These patterns can protect or destabilize orbits depending on the details. Around Jupiter, such effects are especially important because the planet's mass makes the repeated pulls strong and persistent over time. This influence does not mean Jupiter controls the solar system alone. The Sun remains overwhelmingly dominant in total mass and central authority. But among the planets, Jupiter acts as the great organizer. It stands near the boundary between the outer giant planets and the inner smaller worlds. And in that position, its gravity helps define the structure of the middle system. This is one reason Jupiter matters so much in scientific models of solar system history. Many models suggest that Jupiter's formation and movement in the young solar system influenced where material gathered, where planets could grow, and how small bodies were distributed. The details of early migration remain an active field of research, but observations and simulations agree that Jupiter must have played a major part. Its local system of moons deepens this impression of planetary dominance. Jupiter has many moons, from tiny irregular captured bodies to some of the largest and most remarkable satellites in the solar system. The four largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons because Galileo observed them in the early 17th century. Each is a world in its own right. Io is intensely volcanic, heated by tidal flexing caused by Jupiter's gravity and its orbital interactions with neighbouring moons. Europa holds a global ocean beneath an icy crust, making it one of the most studied places in the search for conditions that might support life. Ganymede is the largest moon in the solar system and possesses its own magnetic field. Callisto preserves a heavily cratered ancient surface that records a long history of impacts. These moons orbit within a gravitational system rich in energy and structure. Tides are especially important. A tide is a stretching effect caused by differences in gravity across an object. Around Jupiter, tides can heat moon interiors, drive geological activity, and sustain hidden oceans. This means Jupiter's importance extends beyond its own atmosphere and magnetic field. It creates conditions on nearby worlds. Its gravity becomes a source of internal energy for moons that would otherwise be frozen into greater stillness. Jupiter also has a faint ring system, though much less obvious than Saturn's. This reminds the observer that rings are not unusual in the outer solar system. What changes is their brightness, thickness, and visibility. Jupiter's rings are made largely of dust and are difficult to see except under favourable conditions. Their faintness again shows that much of the solar system's structure is subtle. Not every important feature appears grand at first glance. Its magnetosphere is the largest planetary magnetic structure in the solar system, extending millions of kilometers into space. It traps charged particles, interacts strongly with the solar wind, and envelops much of the region around the planet. Within this invisible domain, radiation levels can be intense. The magnetosphere also connects Jupiter to some of its moons, especially Io, whose volcanic activity supplies material that becomes ionized and feeds a torus, or donut-shaped ring, of charged particles around the planet. Here again, a local planetary system becomes more than a planet alone. It becomes a network of interacting bodies, fields, and matter. Yet however dominant Jupiter may be among the planets, it does not erase the emptiness around it. The gap between Jupiter and Saturn is vast. The gap between Jupiter and Mars inward is also immense. Its moons are spread across large distances. Its magnetosphere, though huge in planetary terms, remains local compared with the scale of the solar system as a whole. Jupiter's greatness is real, but it must be kept in proportion. It is the largest planet, not a second sun. It shapes much, but it does so from within an even larger framework ruled by the Sun and defined by enormous open space. In Jupiter's realm, the solar system reaches a kind of middle weight, where mass, motion, and structure become especially clear. The giant planet turns quickly, carries a deep and violent atmosphere, holds a family of major moons, and exerts gravity strong enough to help sculpt the regions around it. Here the inward journey passes through the most powerful planetary domain, and still, the same quiet lesson endures. Even the solar system's greatest planet moves through an orbit of astonishing size, surrounded not by crowding, but by distance. Inside the orbit of Jupiter, the solar system passes into a region often imagined incorrectly. The asteroid belt has entered popular thought as a crowded zone of tumbling rocks, a place where spacecraft must dodge through dense debris. The real asteroid belt is nothing like that. It is a broad region between the orbits of Jupiter and Mars, filled with many bodies of different sizes, yet spread across such a vast volume of space that the average distance between substantial objects is enormous. A spacecraft crossing the belt is not threading through a stone storm. It is passing through a mostly empty region where individual asteroids are far apart, and direct encounters are unlikely unless deliberately sought. This belt occupies the middle ground between the giant outer planets and the compact inner rocky worlds. It circles the Sun at distances roughly between 2 and 3.5 astronomical units. Even that span, which may sound modest compared with the outer solar system, represents a vast annular region. The belt is not a narrow line, it is a wide band around the Sun, and its members do not all follow the same path. Some orbit closer to the inner edge, some nearer the outer edge, and many travel on slightly tilted or modestly elongated paths. The overall structure remains flatter than the distant scattered populations beyond Neptune, but it is still a three-dimensional region, not a painted ring on a flat page. The bodies within the asteroid belt are remnants from the early solar system. They are pieces of material that never combined into a full planet. In the early disk around the young Sun, dust and rock collided and merged into larger and larger bodies. In some regions, this process continued until planets formed. In the asteroid belt region, that growth appears to have been disrupted. Jupiter's gravity is the main reason. Its immense mass stirred the motions of nearby small bodies, increasing their speeds relative to one another. When collisions happen too fast, bodies tend to break apart or erode instead of merging gently. Over time, this prevented a major planet from forming there. This does not mean the belt is made only of rubble from a destroyed world. That old image is not supported by modern understanding. The belt is better described as a population of leftover building material, altered by collisions, heating, and orbital reshaping over billions of years. Some bodies are primitive and preserve clues to early solar system chemistry. Others have been melted or differentiated in the past. Differentiation is the process by which a body separates into layers, with denser material sinking inward and lighter material rising outward. Much as Earth formed a core, mantle, and crust, the largest asteroids show evidence that some of this internal evolution occurred early, powered by heat from radioactive decay and impacts. Ceres is the largest body in the belt and is classified as a dwarf planet. It is rounded by its own gravity and contains large amounts of water-rich material. Observations from the Dawn spacecraft show that Ceres is not simply a dry rock but a complex world with salts, ice-rich components, and signs of geological processes that continued long after its formation. Vesta, another major body studied by Dawn, is different. It appears more like a protoplanet, a partially formed world with a basaltic surface shaped by ancient melting and huge impacts. These two objects alone show that the asteroid belt is not uniform. It contains bodies with different histories, compositions, and internal structures. Most asteroids are much smaller. Some are rocky, some rich in carbon-bearing material, and some more metal-rich. These broad categories reflect differences in composition and in the temperature conditions under which the material formed in the early solar system. Carbon-rich asteroids are generally darker and more primitive. Silicate-rich asteroids are stonier. Metal-rich ones may represent fragments of the cores of bodies that were once larger and later shattered. Yet all of them, regardless of type, remain separated by large distances. This is the fact that corrects the familiar myth. The asteroid belt contains many objects, but it does not contain crowding in the ordinary sense. Jupiter's gravity still shapes the belt today. Certain orbital distances are depleted because repeated gravitational nudges from Jupiter make those paths unstable. These are called Kirkwood gaps. A gap here does not mean a clean empty lane with nothing at all inside it, but rather a region where stable long-term occupation is less common. Again, resonance is important. When an asteroid's orbital period falls into a simple ratio with Jupiter's, repeated tugs can gradually change its orbit. Over long spans of time, the body may be moved elsewhere, thrown into a new path, or sent inward toward the inner solar system. In this way, the asteroid belt is not only a leftover zone but also a source region for many near-Earth asteroids and meteorites. Meteorites found on Earth often come from the asteroid belt. Impacts within the belt can break fragments from larger bodies. Some of these fragments are then nudged into orbits that cross the paths of the inner planets. This provides scientists with direct samples of early solar system material. In laboratories on Earth, these meteorites reveal chemical and isotopic information about the age and formation of planetary matter. The asteroid belt therefore acts as an archive. Not merely a region of debris, it preserves matter from early solar system history while also sending small pieces inward where they can be studied closely. The belt also shows how misleading diagrams can be. In textbooks, planets and belts must be drawn close together to fit on a page. This often creates the false impression that the asteroid belt is a dense intermediate wall between Jupiter and Mars. In reality, the belt's total mass is small, far less than the mass of Earth's moon. Most of that mass is concentrated in a few large bodies, while the rest is distributed among countless smaller ones. If the material of the entire belt were gathered together, it would still not make a major planet. The importance of the asteroid belt lies not in total quantity, but in history, composition, and position. Its position is crucial. The asteroid belt marks a transition. Beyond it, giant planets dominate the architecture of the solar system. Inside it, the rocky planets orbit in a more compact and sunlit region. Here the scale begins to shift more noticeably toward the inner system. The sun becomes brighter, orbital periods shorten, planetary spacing, though still vast by human standards, becomes less immense than in the outer system. The belt is therefore a bridge, but it is a very empty bridge. A dispersed middle zone shaped by failed planet formation and by the long reach of Jupiter's gravity. In this region, the true scale of the solar system becomes especially clear through contrast. Many asteroids exist, yet there is room almost everywhere between them. A broad belt sounds solid, yet it is mostly vacuum. The mind expects clutter, but nature offers separation. The asteroid belt is not a wall of stone. It is a sparse record of interrupted growth, held in orbit around the Sun between two very different planetary realms. Here, more than in many other places, the solar system teaches that the appearance of abundance can still rest upon profound emptiness. Inside the asteroid belt, the solar system begins to feel more compact, though compact is only a relative word. The distances remain immense by any human measure. Even here, between the belt and the Sun, worlds do not sit close together in any ordinary sense. Yet compared with the giant outward spacing of Jupiter, Saturn, Uranus, and Neptune, the inner planetary region gathers itself more tightly. Mars stands at the outer edge of this inner arrangement. It is the last of the rocky planets when moving inward from the asteroid belt, and its orbit forms a natural threshold between the broad middle system and the brighter, denser region closer to the Sun. Mars circles the Sun at an average distance of about 1.5 astronomical units. This places it far closer to the Sun than Jupiter and distinctly inward of the asteroid belt's main body. Sunlight here is much stronger than in the outer solar system, though still less intense than at Earth. The planet completes one orbit in about 687 Earth days, so a Martian year is nearly twice as long as one on Earth. This shortening of orbital period is part of the inward pattern. As the distance to the Sun decreases, orbital speed rises and the years contract. The solar system does not suddenly become small, it simply begins to move with a faster rhythm. Mars is a rocky planet, smaller than Earth in both diameter and mass. Its surface is solid, marked by craters, volcanoes, valleys, dunes, plains, and polar caps. This surface gives Mars a more familiar quality than the giant planets. It is a world with ground, horizons, and weather that can be imagined more easily in human terms. Yet its familiarity should not hide the scale of its setting. Mars still moves through an orbit of enormous size around the Sun. The empty space between Mars and Earth, or between Mars and the inner edge of the asteroid belt, remains vast enough to dwarf all travel known in ordinary life. Even the nearest planetary neighbours are separated by distances that change constantly as each follows its own path around the Sun. The reddish colour of Mars comes from iron-rich minerals weathered into rust-like oxides in the soil and dust. Its atmosphere is thin, composed mostly of carbon dioxide, with traces of nitrogen, argon, and water vapour. Because the atmosphere is so sparse, it offers only limited protection from temperature extremes and radiation. Heat escapes quickly, and daily temperature changes can be large. Liquid water is not stable at the surface under most present conditions, though water ice is abundant in the polar caps and underground in many regions. Observations indicate that ancient Mars once had flowing liquid water on its surface, with rivers, lakes, and perhaps transient seas, valley networks, sedimentary layers, and mineral deposits all support that picture. It remains uncertain exactly how long warm and wet conditions persisted and how often they returned. This ancient water history makes Mars especially important scientifically. It appears to preserve a record of planetary change that reaches back to the early solar system. The planet likely formed from the same general rocky material as Earth and Venus, yet followed a different path. Its smaller size meant it lost internal heat more quickly. Its magnetic field, which once existed globally, faded early. Without a strong global magnetic shield, the upper atmosphere became more vulnerable to stripping by the solar wind. Over long periods, much of the atmosphere was lost. The planet dried, cooled, and became the cold desert world seen today. This story is still being refined, but the broad outline is strongly supported by evidence from orbiters, landers, and meteorites. The physical scale of Mars itself adds another lesson about the solar system. The planet hosts the largest volcano known in the solar system, Olympus Mons, and one of the largest canyon systems, Valles Marineris. These features are immense by planetary standards. Olympus Mons rises far higher than any mountain on Earth, and Valles Marineris stretches across a distance that would cover a large fraction of Earth's diameter. Yet even such colossal landmarks exist on a world that is small compared with Earth, and Mars itself remains tiny compared with the size of its orbit. A planet can contain monumental geology while still being a small point in the wider architecture of the solar system. Mars has two small moons, Phobos and Deimos. They are irregular in shape and much smaller than Earth's moon. Their origin remains uncertain. Observations suggest they may be captured asteroids or the result of debris from a giant impact, but no single explanation has been confirmed with complete confidence. Whatever their origin, They underline the modest scale of the Martian system compared with the great moon families of the outer giants. Mars does not rule a large local empire. It moves with two small companions through a quiet orbital region lit by a stronger sun than the outer planets receive, yet still surrounded by vast emptiness. Its seasons arise from a rotation axis tilted by about 25 degrees. Similar in broad effect to Earth's, polar caps grow and shrink with the seasons, and fine dust can be lifted into the atmosphere by winds, sometimes creating local storms and sometimes growing into planet-wide dust events. These storms do not fill the space around Mars. They remain surface and atmospheric phenomena, important to the planet itself but minute compared with the scale of the orbit in which Mars travels. This contrast between local drama and cosmic emptiness recurs throughout the solar system. A planet can be active, varied, and dynamic, while its broader setting remains dominated by silence and distance. Mars also marks an observational boundary in human culture. It is one of the easiest planets to study from Earth, and one of the few whose surface has been mapped in extraordinary detail by orbiters and rovers. Because of this, it often feels close in thought. But mental closeness is not physical closeness. When Mars and Earth are favourably aligned, they can approach one another more closely than at other times. Yet even then the gulf between them remains severe. Radio signals take minutes to cross the distance. Spacecraft require months to travel there using current technology. Nearness, in solar system terms, is still far beyond everyday scales of movement and communication. This region around Mars therefore represents a narrowing, but not a collapse, of scale. The giant planets now lie outward behind, and the Sun has become more visually and physically dominant. Orbital periods are shorter, sunlight stronger, and rocky surfaces more immediate. Yet the structure of the solar system remains faithful to its deepest rule. Matter is gathered into isolated worlds set within huge volumes of mostly empty space. Mars, as the outermost rocky planet, holds the line between the sparse middle system and the inner family of terrestrial worlds. It shows the transition clearly. The distances are becoming more graspable, but they are not becoming small. The solar system is still wide, and Mars moves through its reddish orbit as a solitary desert world at the edge of the brighter inner realm. Inside the orbit of Mars, the solar system enters the region of Earth and its moon. This is the first place in the inward journey where human experience provides direct scale. Yet it is also one of the places where intuition is most misleading, because Earth is home, and because the moon appears large in the sky. The Earth-Moon system can seem compact and familiar. In reality, even this nearest celestial relationship is defined by striking emptiness. Earth and the Moon are close only in comparison with other planetary distances. By ordinary standards, they are separated by an immense gulf of space, wide enough to contain all the other planets between them in a simple diameter comparison. Familiarity has the power to shrink what is in fact enormous. Earth orbits the Sun at an average distance of 1 astronomical unit. This unit is based on Earth's orbit because Earth provides the reference from which the scale of the solar system was first measured with confidence. At this distance, sunlight is strong enough to warm the planet, drive weather and climate, sustain surface liquid water, and support the chemistry of life. Earth completes one orbit in 1 year, the basic seasonal cycle known through agriculture, calendars, and history. Inward from Mars, the shortening of orbital period becomes even clearer. The Sun now occupies a more commanding place in the sky, and its energy shapes the surface and atmosphere continuously. Yet Earth's orbit is still vast. The path around the Sun measures hundreds of millions of kilometers in length. and Earth moves along it at tremendous speed while living things at the surface remain unaware. Earth is a rocky planet with a layered interior, an active geology, a dynamic atmosphere, and a global ocean. Its outer shell is broken into moving tectonic plates. A tectonic plate is a large piece of the rigid outer layer of a planet that moves slowly over the softer material below. This motion reshapes continents, raises mountains, opens ocean basins, and helps recycle carbon through the crust and mantle. Earth's magnetic field, generated by motion in its liquid outer core, helps shield the atmosphere and surface from much of the charged particle flow coming from the Sun. These features give Earth a special place among known planets, but they do not change the lesson of scale. Earth may be rich in water, air, and life, yet it remains a small sphere moving through a broad orbital lane around one ordinary star. The Moon is Earth's natural satellite and the nearest major celestial body beyond Earth itself. Its average distance from Earth is about 384,000 kilometers. This number is large enough that light takes more than 1 second to travel one way between Earth and the Moon. Human missions that reached the lunar surface needed days to make the journey. In the night sky, the Moon looks almost within reach because it appears large and bright. That appearance arises from nearness relative to other celestial objects, not from actual closeness in human terms. The space between Earth and the Moon is real, deep, and mostly empty. This local emptiness is one of the clearest corrections to ordinary intuition about the solar system. The Moon likely forms after a giant impact early in Earth's history. In the leading model, a Mars-sized body collides with the young Earth, and material from both bodies is thrown into orbit and later gathers into the Moon. This model explains many features of the Earth-Moon system, including the Moon's composition and the angular momentum of the pair. Some details remain under study, but the broad impact origin is strongly supported. The result is a system unlike the giant planets with their many moons. Earth has one large companion, unusually large relative to the planet it orbits. This has important effects. The Moon raises tides in Earth's oceans and crust, gradually slows Earth's rotation, and helps stabilize the tilt of Earth's axis over long periods, which in turn influences climate stability. Tides provide a useful example of how gravity works across space. The Moon pulls more strongly on the near side of Earth than on the far side, creating a stretching effect. This produces ocean tides, modulated also by the Sun. The same physics acts throughout the solar system, but in the Earth-Moon system it can be observed directly and felt in daily life. Over immense stretches of time, tidal interaction transfers energy and angular momentum. The Moon slowly moves farther away from Earth by a few centimeters each year. Earth's day slowly grows longer. These changes are tiny within a human lifetime, yet they reveal a long and continuous dynamical relationship unfolding across empty space. The Moon itself is a rocky world with ancient volcanic plains, heavily cratered highlands, and no substantial atmosphere. Because there is almost no air, the sky above its surface is black even in daylight, and temperature differences between sunlit and shadowed areas are extreme. It preserves a record of impact history more clearly than Earth does because it lacks weather, flowing water, and plate tectonics to erase old scars. The lunar surface therefore serves as an archive of early solar system bombardment. Samples returned by astronauts and robotic missions show a history reaching back more than 4 billion years. In this way, the nearest world also becomes one of the oldest visible records available to direct study. From the point of view of solar system scale, the Earth-Moon system teaches 2 lessons at once. First, it shows that local space is far larger than daily perception suggests. Second, it shows that even within that emptiness, gravitational relationships can be intimate and powerful. Earth and the Moon do not need to be close in the ordinary sense for each to shape the other profoundly. Their mutual orbit around a shared centre of mass, located inside Earth but offset from its centre, is a reminder that even a familiar planetary pair is a dynamic system of motion, not a static picture. Earth's neighbourhood also includes artificial satellites, occasional passing asteroids, and the broader influence of the Sun through sunlight, the solar wind, and changing magnetic conditions in near-Earth space. Yet none of this fills the surrounding void. Space near Earth is not crowded when judged by true scale. Thousands of satellites may orbit the planet, but the volume around Earth is so great that emptiness remains the dominant fact. This same principle extends outward to the planets. Count alone does not defeat space. The solar system remains sparse even where activity appears dense. Inward from Mars, Earth marks a powerful shift in the journey, because it is a place where scale can finally be compared with lived experience. The sun is bright and warm. The year is familiar. The moon is visible to the unaided eye and reachable with human machines. Yet all of this closeness is relative. Earth still travels around the sun through a huge orbit. The moon still circles Earth across a gulf far wider than instinct suggests. The Earth-Moon system therefore becomes one of the most effective demonstrations of the solar system's true nature. Even at home, even in the most familiar celestial arrangement, the architecture is built not from nearness, but from distance, motion, and the quiet rule of open space. Inside Earth's orbit, the solar system moves into the brighter region of Venus. Here the sun becomes more intense. The pace of orbital motion increases, and the distinction between the comfortable conditions of Earth and the harsher realities of planetary physics becomes clearer. Venus circles the Sun at an average distance of about 7/10 of an astronomical unit. This is close enough to the Sun that the planet receives roughly twice the solar energy that reaches Earth. The effect of that stronger sunlight is profound, though not in a simple or isolated way. Venus shows that distance from the Sun matters greatly, but also that atmosphere, chemistry, clouds, and planetary history decide how that energy is experienced at the surface. Venus takes about 225 Earth days to complete one orbit. Its year is therefore shorter than Earth's. This fits the inward pattern already established. As the distance to the Sun decreases, orbital speed rises and the length of the year contracts. The planet moves through a path around the Sun that is still enormous by human standards, yet clearly smaller than Earth's orbit. In drawings of the inner solar system, the paths of Venus and Earth often appear close together, almost like neighbouring tracks. In reality, the space between those orbits remains immense. Venus is the nearest planet to Earth in broad average terms over long spans, but nearness here still means tens of millions of kilometres, even under favourable alignment. The inward tightening of the solar system does not erase vastness. It only makes the vastness more concentrated. Venus is similar to Earth in size and overall rocky composition, which is why the two planets are often called sisters in a broad descriptive sense. Their diameters are close, their masses are comparable, and both are terrestrial planets, meaning they're built primarily of rock and metal rather than hydrogen and helium. Yet their present states are dramatically different. Venus possesses a dense atmosphere composed mostly of carbon dioxide, with clouds of sulfuric acid high above the surface. The atmospheric pressure at the surface is crushing, and temperatures are hot enough to melt lead. This extreme heat comes not only from being closer to the Sun, but from an intense greenhouse effect. A greenhouse effect occurs when a planet's atmosphere allows sunlight to enter more easily than heat can escape, causing warming at the surface and lower atmosphere. On Venus, this process is powerful and persistent. The clouds of Venus reflect much of the sunlight that strikes the planet, making it one of the brightest objects in Earth's sky. This brightness can create the false impression of coolness, because bright white clouds suggest freshness to human intuition. In fact, the cloud deck hides a severe world beneath. The upper atmosphere is bright and reflective, but below it lies a deep layer of hot, dense gas that traps heat with extraordinary efficiency. This hidden contrast is one of the reasons Venus matters so much in comparative planet science. It shows how a planet of Earth-like size can evolve into a radically different environment under the combined effects of solar input, atmospheric composition, and geologic history. The surface of Venus is rocky and varied, though difficult to observe directly because the cloud cover is opaque to visible light. Radar mapping from orbit has revealed broad volcanic plains, large shield volcanoes, deformed uplands, and complex tectonic patterns. The surface appears relatively young in a geological sense, with many signs of volcanic resurfacing. Exactly how often volcanic activity occurs on Venus today remains uncertain, but observations indicate that the planet may still be geologically active. Some data suggest recent volcanic changes and the presence of active interior processes, though the full picture is still being refined. What is clear is that Venus is not a dead stone sealed beneath clouds. It is a planetary system of atmosphere, crust, mantle, and possible ongoing activity. Its rotation adds another layer of difference. Venus spins very slowly and in the opposite direction from most planets in the solar system. This is called retrograde rotation. In practical terms, the Sun would appear to rise in the west and set in the east if the thick clouds were not in the way. A single rotation of Venus relative to the stars takes longer than its year. This unusual rhythm means that the relation between day and year is unlike that of Earth or Mars. The causes of this slow backward rotation are still debated. Early collisions, atmospheric tides, and long-term solar effects may all have contributed. The exact history remains uncertain. Despite this slow spin, the upper atmosphere of Venus moves rapidly. Winds at cloud top level circle the planet much faster than the solid body rotates beneath. This phenomenon is called superrotation. It means the atmosphere has its own strong global motion, driven by solar heating, pressure gradients, and complex circulation. The result is a world where the visible outer layer is in swift motion, while the planet itself turns with extreme slowness. This difference between atmospheric tempo and planetary rotation adds to the strange character of Venus as an inner world shaped by the Sun yet not simplified by that closeness. Venus has no moon. This absence gives its local system a solitary quality. Earth has the moon as a nearby companion, a visible partner shaping tides and stabilizing axial behavior. Venus travels alone through its orbit. That solitude, however, does not make its environment simple. The interaction between the atmosphere and the solar wind is significant, because Venus lacks a strong global magnetic field like Earth's. Instead, the solar wind interacts more directly with the upper atmosphere, inducing magnetic effects and contributing over long timescales to atmospheric escape. Even here, close to the Sun, the relationship between a planet and surrounding space remains active. From the point of view of scale, Venus teaches that the inner solar system is not merely a warmer version of the outer one. It is a region where solar energy increasingly shapes planetary character. The Sun appears larger and brighter in the sky of Venus than it does from Earth. Light and heat become stronger agents. Yet the orbit remains huge. The surrounding space remains mostly empty, and the separation from neighbouring planets remains vast. This combination of stronger solar force and persistent emptiness defines the inner system. The worlds are closer to the Sun, not close in any ordinary earthly sense. Venus also helps correct another quiet misconception. Similar size does not mean similar fate. Two planets can begin with roughly comparable bulk properties and still diverge profoundly. Venus and Earth likely formed from related materials within the same general inner solar system environment. Over time, differences in atmosphere, water history, volcanic cycling, and solar interaction lead them along distinct paths. Venus may once have had more temperate conditions, perhaps even shallow water. But current evidence cannot yet establish the exact extent or duration of such an early state. What can be said with confidence is that the modern planet is overwhelmingly hostile by Earth standards, wrapped in cloud, compressed by heavy air, and heated far beyond ordinary habitability. In this region, the solar system feels more intense. The sun grows nearer, the year shortens, light dominates appearances, and cloud becomes a mask over a severe world. Yet the old law still holds. Venus is a single planet moving through an immense orbit in a largely empty volume of space. Its brightness in the sky does not mean closeness in the human sense. Its nearness to Earth remains a gulf. Its nearness to the Sun remains part of a scale still far beyond instinct. Venus stands as a brilliant inner marker, showing how quickly conditions change as one moves sunward, while the architecture of distance remains firm and immense. Inside the orbit of Venus, the solar system reaches the path of Mercury. This is the innermost orbit of the major planets. The last broad ring before the Sun itself becomes the central focus. Mercury circles at an average distance of about 4/10 of an astronomical unit from the Sun. In simple comparison with the outer planets, this seems very close. Yet even here, closeness must be handled carefully. The distance from Mercury to the Sun is still tens of millions of kilometers. The inward journey has compressed the planetary system greatly compared with the wide outer reaches, but it has not made it small. Mercury moves through an orbit of enormous size around a star that now fills much more of the sky and governs conditions with far greater intensity than at any planetary region already crossed. Mercury completes one orbit in only 88 Earth days. Its motion around the Sun is the fastest of any major planet. This rapid orbital period reflects both its small orbital path and the strong gravitational pull it experiences so near the solar system's central mass. The inward pattern now becomes unmistakable. Years have steadily shortened from Neptune inward, and at Mercury they contract to less than 3 months in Earth terms. Yet the shortening of the year does not mean simple daily life on the planet. Because Mercury's rotation introduces a more complicated rhythm, it spins slowly relative to the stars, completing one rotation in about 59 Earth days. Because of the relationship between its spin and orbit, one solar day on Mercury, meaning one noon to the next, lasts much longer than its year. The timing of light and darkness is therefore prolonged and severe. Mercury is a rocky planet, but unlike Earth, Venus, or Mars, it has only a very thin exosphere rather than a substantial atmosphere. An exosphere is an extremely sparse outer layer where atoms and molecules are so widely spaced that they rarely collide. On Mercury, this fragile envelope contains atoms such as sodium, potassium, oxygen, and helium, supplied by the solar wind, surface impacts, and the slow release of material from rocks. Because the atmosphere is so thin, it cannot hold heat efficiently or soften the incoming force of sunlight. As a result, Mercury experiences extreme temperature contrasts between day and night. Sunlit regions become intensely hot, while dark regions can become extremely cold. These changes are not moderated by thick air, clouds, or weather systems as they are on Earth or Venus. The surface of Mercury is heavily cratered and ancient in appearance, resembling the Moon in some broad visual respects. Great impact basins, long cliffs, smooth volcanic plains, and densely marked highlands testify to a long history of bombardment and planetary change. One of the most striking features is the presence of scarps, which are long cliffs formed as the planet cools and contracts over time. This contraction suggests that Mercury's interior has lost heat and shrunk enough to wrinkle the crust. The planet therefore remains geologically meaningful, not merely a static relic. It is small, but it preserves evidence of both violent external impacts and slow internal evolution. Mercury's composition is unusual among the rocky planets. It has an exceptionally large iron-rich core relative to its total size. This makes the planet denser than would be expected for a rocky world of its small diameter alone. The reason for this large core remains uncertain. One possibility is that Mercury originally forms with more metal-rich material near the young Sun. Another is that a giant impact strips away much of an earlier rocky outer layer, leaving a metal-heavy remnant. Current evidence supports the large core itself, but the exact path by which Mercury acquires it is still debated. What matters in the present inward journey is that Mercury reveals strong variation even within the small family of inner rocky worlds. Nearness to the Sun does not produce uniformity, it produces another distinct outcome. Because Mercury lies so close to the Sun, the star appears far larger and brighter in its sky than it does from Earth. Sunlight there is fierce. The solar energy reaching Mercury is several times stronger than at Earth. Yet the lack of a thick atmosphere means this intense sunlight affects the surface directly, rather than being diffused through clouds or dense air. Shadows are sharp. The contrast between illuminated and dark terrain is severe. The Sun dominates the visual and thermal environment in a way that becomes difficult to ignore. Mercury is therefore a place where the solar system's inner compression becomes emotionally clearer. The Sun is no longer only the distant source of planetary motion, it becomes a looming local presence. Even so, Mercury's orbit remains a substantial path in space, not a tight circle hugging the Sun like a bead on a wire. Its orbit is also more elongated than those of most major planets, meaning its distance from the Sun changes significantly over the course of a year. This variation affects the amount of sunlight reaching the surface and contributes to the complexity of solar days and surface heating. Mercury also experiences a measurable precession of its orbit, meaning the orientation of the orbit slowly shifts over time. Part of this effect is explained by the gravitational influence of other planets, but an additional part became one of the classic early tests of Einstein's general theory of relativity. In this way, Mercury helps reveal not only planetary science, but also deeper features of gravity itself. The planet has no moon and no ring system. Its local setting is solitary. It moves alone through the innermost planetary region, accompanied only by the sparse dust and charged particles that exist throughout inner solar system space. Yet solitude does not mean simplicity. Mercury possesses a magnetic field, though much weaker than Earth's. This field creates a small magnetosphere that interacts with the solar wind. The existence of the field indicates that part of the planet's metallic interior remains active in ways that generate magnetic structure. Thus even this small scorched world maintains a dynamic relation with surrounding space. One of the quiet surprises of Mercury is that water ice exists in permanently shadowed craters near the poles. At first, this seems impossible on a world so close to the Sun. Yet where deep crater floors never receive direct sunlight, temperatures can remain low enough for ice to persist over long timescales. Radar observations and spacecraft data support the presence of such deposits. This fact provides an important lesson. Solar distance is powerful, but local geometry also matters. Even on the innermost planet, cold traps can preserve volatile material if sunlight is excluded continuously. Mercury marks the final planetary step before the solar system turns fully toward the Sun itself. Here the planets have become tightly packed only by comparison with the outer system. The actual distances remain immense. Mercury's path around the Sun is still huge. The gap between Mercury and Venus remains vast. The surrounding space is still overwhelmingly empty. Yet the inward compression is now undeniable. Orbital speeds are high, years are short, and the Sun's physical presence has become overwhelming. Mercury shows how the inner edge of the planetary system works not as a cramped place of crowding, but as a region where distance narrows enough for solar power to dominate, while the grand emptiness of space still remains intact. At the center of the planetary system stands the Sun. After moving inward through the distant clouded boundaries, the icy belts, the giant planets, the asteroid region, and the rocky inner worlds, the solar system now arrives at the one object that gives the whole structure its meaning. The Sun contains almost all the mass in the solar system. The planets, moons, asteroids, comets, dust, and gas together make up only a small remainder. This fact is more important than any image of size alone. The Sun is not merely the brightest object in the solar system. It is the dominant physical reality, the great central reservoir of mass whose gravity holds the rest in orbit, and whose light and heat shape conditions across every region already crossed. The Sun is a star, one among the many hundreds of billions in the Milky Way. Yet for the solar system it is everything. It is a nearly perfect sphere of hot plasma, plasma being matter so hot that electrons are no longer bound tightly to atomic nuclei. In this state, the gas responds strongly to magnetic fields and supports the complex flows and eruptions seen at the solar surface and above it. The Sun forms about 4.5 billion years ago from the collapse of a region within a molecular cloud, a cold cloud of gas and dust in interstellar space. As gravity pulls the material inward, most of the mass gathers at the center, where pressure and temperature rise until nuclear fusion begins. Fusion is the process in which light atomic nuclei join together to form heavier ones, releasing energy. In the Sun, hydrogen fuses into helium in the core, and that steady reaction powers the star. The scale of the Sun is difficult to absorb because it overwhelms comparison. Its diameter is about 109 times that of Earth. More than 1 million Earth-sized volumes could fit inside it. Its mass is about 333,000 times that of Earth. Yet even these numbers, large as they are, do not fully explain the Sun's central role. What matters most is proportion. The Sun contains about 99.8% of the total mass of the solar system. This means that almost everything that moves around it does so under the rule of a single object that vastly outweighs the rest combined. The planets may seem like the main cast in drawings and in cultural imagination, but physically they are secondary. The solar system is first and foremost a star system. The energy produced in the Sun's core begins a long journey outward. In the core, pressures and temperatures are high enough for hydrogen nuclei to overcome their mutual repulsion and fuse. The energy released emerges first as gamma rays and particle motion. It does not pass straight to the surface in a quick line. Instead, it is absorbed and re-emitted many times in the radiative zone, the region where energy moves mainly through radiation. Farther outward lies the convective zone, where hot plasma rises, cools, and sinks again in great circulating currents. By the time energy reaches the visible surface, called the photosphere, it has changed character into the sunlight that illuminates the planets. From there, light crosses the space to Earth in about 8 minutes. To Neptune, it takes several hours. This delay quietly demonstrates both the speed of light and the scale of the solar system at once. The visible surface of the Sun is not solid. It is the level from which light escapes most freely into space. Above it lies the chromosphere and then the corona, the Sun's extended outer atmosphere, which reaches into space and is visible during total solar eclipses as a pale halo. The corona is extraordinarily hot, much hotter than the visible surface below, a fact that remains one of the important puzzles of solar physics, though magnetic processes are strongly implicated. From the corona flows the solar wind, a continuous stream of charged particles moving outward through the solar system. This wind helps create the heliosphere, the broad bubble already encountered in the outermost view. In this way, the Sun is not only a bright central body, it also extends itself outward as a field of particles and magnetic influence that reaches far beyond the planets. Solar magnetism gives rise to many of the Sun's changing features. Sunspots, darker cooler regions on the photosphere, appear where magnetic fields emerge strongly through the surface. Flares release bursts of energy. Coronal mass ejections throw huge clouds of charged particles into space. These events are tied to the solar cycle, an approximately 11-year variation in magnetic activity. The Sun is therefore not a constant lamp in every detail. Its total light output changes only slightly across the cycle, but its magnetic behavior can vary markedly, affecting space weather throughout the solar system. On Earth, strong solar events can influence auroras, satellites, radio systems, and electrical infrastructure. On other planets, the same solar activity interacts with atmospheres, magnetospheres, and surfaces in different ways. The Sun's size can be misunderstood in two opposite directions. In some simplified diagrams, it is drawn only a little larger than the planets, so the rest of the system can fit on a page. In that form, its true bulk is hidden. In other contexts, its great diameter is rightly emphasized, but its relation to distance is then lost. Both truths need to be held together. The Sun is enormous compared with any planet, yet the spaces separating it from the planets are also enormous. If the Sun were reduced to a more manageable scale in imagination, the planets would become tiny indeed, and would still have to be placed very far away. The solar system is not large because the Sun alone is large. It is large because a very large star sits at the center of even larger distances. Its gravity defines the basic motion of every major body in the system. The planets orbit because they move forward through space, while the Sun's gravity bends that motion into repeated paths. Comets plunge inward and outward along elongated routes under the same rule. Dust grains spiral gradually inward under sunlight and drag effects. Even the distant bodies of the scattered disk and Oort cloud remain, in some degree, under solar command. Yet gravity is not the whole story. The Sun also establishes thermal zones. Close to it, volatile substances struggle to remain frozen. Farther out, ices survive. This difference shapes planetary composition from Mercury to Neptune. The Sun therefore governs not only motion but also chemistry and structure. To understand the solar system at its core is to understand that the planets are products of the Sun as much as companions to it. They form from the disk of material around the young star. Their compositions reflect temperature gradients set by solar distance. Their climates depend on received sunlight, internal heat, and atmospheric evolution. Their years exist only because of solar gravity. Their surfaces bear the marks of solar radiation, solar wind, and the changing energy of the central star. The Sun is not simply located in the middle. It is the active source from which the system's order flows. At this inward point, after crossing every outer and middle region, scale becomes clearer in a final way. The Sun is so large that the planets seem secondary, and yet the empty distances around it are so great that even this giant star does not fill the system in any visual sense. It dominates by mass and energy, not by physically occupying most of the volume. The solar system is therefore a striking combination of concentration and emptiness. Nearly all its mass sits in one central star. Nearly all its volume is open space. The Sun reveals both truths at once. It is the overwhelming center, and it rules a domain that remains in almost every direction, mostly void. At the innermost point of this journey, with the Sun established as the central mass and source of light, the full scale of the solar system can be considered from within rather than from outside. What becomes clear is not crowding, but spread. The solar system contains planets, moons, belts, clouds, dust, gas, magnetic fields, and moving streams of charged particles. Yet its most defining physical feature is emptiness. Matter is concentrated into separate bodies and thin structures, while the overwhelming majority of the system's volume consists of space through which those bodies move. This truth remains constant from the outer cloud to the orbit of Mercury, but it is easiest to recognize here, once the whole structure has been crossed in orderly inward motion. The human mind often builds its understanding of size through comparison with rooms, roads, mountains, and oceans. Such comparisons fail quickly in astronomy because the scale changes by many orders of magnitude, while the governing patterns remain simple. A planet can be large enough to swallow continents in imagination, yet tiny compared with the span of its orbit. A ring system can appear broad and magnificent, yet remain thinner than a mountain range when compared with its width. A belt of countless bodies can sound dense and still be mostly vacuum. Even the Sun, which contains nearly all the mass of the solar system, occupies only a small central fraction of the total volume, enclosed by the orbits and distant reservoirs associated with its gravity. The system is therefore not built as a filled machine. It is built as a wide gravitational arrangement in which separate concentrations of matter trace long paths through open dark. This open dark is not nothing in the philosophical sense. Space within the solar system contains sunlight, magnetic fields, the solar wind, dust grains, occasional atoms, and the curved geometry through which gravity acts. But in terms of ordinary matter packed close enough to touch, space remains almost entirely empty. That emptiness is why motion on the solar system scale can persist so smoothly. Planets do not need cleared roads. They need only gravity and momentum. A planet in orbit is always falling toward the Sun while also moving forward fast enough to continue missing it. That balance creates the repeated path. Because space is so empty, these paths remain open across immense distances and immense spans of time. Seen from this inward understanding, each region visited earlier becomes part of one continuous pattern. The Oort cloud, though uncertain in detail, suggests the outer fading reach of solar gravity in all directions. The scattered disk preserves the long memory of gravitational scattering. The Kuiper belt holds a cold disk of separated remnants beyond Neptune. The giant planets occupy wide orbital lanes, each carrying its own local system of moons, rings, and invisible magnetic influence. The asteroid belt marks interrupted planetary growth without ever becoming a wall of stone. The rocky planets move in the brighter inner zone, closer together in relative terms but still isolated by severe gulfs of space. The Moon circles Earth across a gap that familiarity tends to shrink in thought. Mercury races around the Sun, yet even its fast, tight orbit remains enormous by all human standards. None of these facts contradicts the others. Together they describe a single architecture of sparse matter arranged across a vast domain. The true scale of the solar system is also temporal. Distances are not merely measured in kilometers or astronomical units. They are measured in travel time for light, in orbital years, in the slow drift of tides, in the migration of planets, in the cooling of interiors, and in the persistence of ancient surfaces. Some worlds rotate in hours, some orbit in decades or centuries. Comets may spend most of their existence in remote darkness and only briefly enter the visible inner system. Geological changes may require millions of years. The Sun itself evolves across billions. Scale, in this sense, is not only the size of space but the length of processes. A large system creates long rhythms. This temporal scale helps explain why the solar system can feel smaller in modern culture than it truly is. Machines cross interplanetary distances. Telescopes resolve distant worlds. Maps give the impression of access. Yet even the most familiar destinations remain far beyond ordinary travel. Radio signals take minutes or hours to move between planets. Spacecraft need months or years to cross distances that, in diagrams, appear as narrow gaps. Precision navigation is required because targets are not standing still. Every world is moving in its own orbit, and every launch is an act of timing within a continuously changing three-dimensional arrangement. The solar system is therefore not only large, it is actively large, always in motion, never presenting the same geometry for long. What the inward journey ultimately reveals is a change in proportion. At first glance, one may think the solar system is a collection of planets with some additional material around them. After careful passage through its regions, that view reverses. The solar system is mostly space, structured by gravity, with planets as small nodes inside it. The planets matter enormously because they are where material gathers into worlds, atmospheres, weather, geology, and sometimes oceans. But in terms of scale, they are exceptions. Space is the rule. This is as true for the gap between Earth and the Moon as it is for the distances between Neptune and the Kuiper belt, or between the Sun and the suspected Oort cloud. This understanding also clarifies why scientific certainty changes with region. The inner planets can be mapped in great detail because they are relatively accessible. The giant planets can be studied by telescopes and occasional spacecraft. Distant icy bodies are fainter and fewer in direct observation. The Oort cloud is inferred rather than surveyed as a whole. This gradient of knowledge follows scale itself. The farther outward matter thins and the larger the volume becomes, the harder it is to observe directly. Yet uncertainty in the details does not weaken the main picture. The broad scientific consensus is firm. The solar system is large beyond ordinary intuition, and its largeness is expressed most powerfully through emptiness, separation, and long governed motion around one star. At the centre, then, the final measure is not a single number. No one figure can carry the whole meaning. The scale of the solar system is the Sun containing almost all the mass, the planets occupying only tiny fractions of their orbits, the belts being sparse, the clouds being remote, and the distances being so great that even light needs time to cross them. It is a structure both simple and difficult to feel. One star, a family of worlds, great intervals between them, a vast outer fading edge. The solar system, properly seen, is not crowded, compact, or tightly filled. It is wide, thin, and ordered, with matter scattered lightly across an enormous and mostly silent expanse. The inward view now grows quiet. The Sun remains at the centre, steady in its long burning, while every planet continues along its own measured path. Mercury moves quickly through fierce light. Venus turns beneath its bright cloud cover. Earth carries ocean, air, and the Moon across a familiar but still immense orbit. Mars follows as a colder red companion farther out. Beyond, the asteroid belt remains thin and dispersed. Jupiter and Saturn keep their great systems of moons and rings in motion. Uranus and Neptune continue in dimmer sunlight, slow and remote. Farther still, icy bodies drift in broad outer populations, and the most distant cloud of comets fades into uncertainty and darkness. Nothing in this system is crowded. The deeper truth is gentler and larger than the eye first expects. Worlds are real, beautiful, and varied, yet each is only a small gathering of matter inside a vast arrangement ruled by gravity. Between them lies open space, not as absence alone, but as the condition that allows motion, timing, season, orbit, and change. The solar system holds its shape because so much of it is empty. This emptiness does not diminish it. It gives the system its grandeur. Light crosses it. Planets circle within it. Moons rise and fall in distant skies. Dust drifts. Comets wait in cold silence for long ages before returning sunward. The whole structure remains thinly spread around one ordinary star in one ordinary part of the Milky Way, and yet it contains enough scale to humble thought and enough order to reward patient attention. The final impression is calm. One star gathers almost all the mass. A family of worlds moves around it. Great distances separate them. Time flows differently from orbit to orbit, but the pattern endures. In that wide and mostly silent expanse, the true size of the solar system is not only measured in numbers, it is felt in the long space between things, in the slowness of far regions, and in the quiet certainty that even the nearest heavens are larger than instinct allows.